Hello and welcome to the second lecture of EGR 2513 Engineering Dynamics Fall 2019. This will be going through section 12.3 of the textbook. We'll be covering erratic motion, and what we're going to be looking at here is ways of looking at the relationship among displacement and velocity and acceleration via graphs. And we know that the relationship among acceleration, velocity, and displacement can really be described in terms of integrals and derivatives. And so what we'll be doing is looking at curves and either looking at the slopes of those curves to get the derivative, or we'll be looking at the area under the curve to get the integral. And so this is one way of visualizing what's going on. One of the graphs that we'll be looking at is a position versus time graph. And so we'll just kind of focus in on this graph here. You can see that we have position S is in the y-axis and time t is in the x-axis. So we're just looking at the position of a particle as a function of time. And so what you can see as we look at this particle, that this particle has a certain position as a function of time, and at any time we can see how far the particle has moved. Now, one of the things that we might want to do from that would be able to come in and compute what the velocity is at any given time point here. And really all we need to do here is, because we know that the velocity is the derivative of position with respect to time, we just need to go in and find a point on the graph, calculate the slope, and we know the velocity at that particular instant. Okay, and so what we would do then is, as you can see, they've methodically gone through here, and for example, at the very beginning here we have a slope for the initial velocity. We can come down to this graph right here. That tells us what the initial velocity is. And then you can see if we go to this next position here, we have the velocity 1. That comes down and corresponds to this point right here. And so here you can see we're just plotting velocity versus time. We're doing it by going through and at discrete time points that are lining up on both of these graphs, we are able to convert the position versus time graph to a velocity versus time graph. And the approach to doing that is just to go through one time point at a time, calculate the slope at those various positions, and then that tells us what the velocity is at those various positions. So that's the approach of working with a position versus time graph. Now, we could also then say, well, we know that the relationship between the velocity and the acceleration is that you can see the acceleration is the derivative of the velocity with respect to time. So what that means then is that if I want to compute the acceleration from the velocity graph here, well, what I would be doing here then would just be to take the slope at the various points along that graph. So it's the same concept that we used before, except that now this is a velocity versus time graph rather than a position versus time graph. And we're going through and looking at various points along this curve. And once we have calculated the slope at those positions, why then we can go then and record those on an acceleration versus time graph. And just remember that this velocity versus time graph, we were able to compute that previously from the position versus time graph by going through at different locations on the position versus time graph, getting the derivatives at those points, and then plotting them on the velocity versus time graph. And you can see that's the same thing that we're doing here, right? We're just going through at various times along this velocity versus time graph that we just constructed, going through and calculating the slope of the curve at those positions, and then we're able to come up with this acceleration versus time graph. And now here we have if we want to come up with the AT graph, what can we do with an AT graph? Well, we know that the acceleration versus time is going to be the derivative of the velocity, and we really don't have anything yet that goes beyond the acceleration. So really all we can do then is to take the acceleration versus time graph, and we'll be able to go in and then take the area under the curve, because if we integrate the acceleration, that's going to give us the velocity. So you can see here's an example where they've done that. They have this acceleration versus time graph right here is the acceleration versus time. And what they've done here is they've looked at one little increment of time, and they said, well, in this increment of time, what is the area under the curve here? So I would just calculate this area, and they've approximated it as this rectangle. And you can see that that change in velocity is going to be here equal to the integral under that curve. So now you can see here that if I know what the initial velocity is, here I have a velocity versus time curve. If I know what the initial velocity is, if I want to know now what the velocity is at the next point in time, I can get the change in that velocity from v0 to v1 as delta v. Delta v is the area under that curve. Okay, so now that we understand that, let's repeat what this process would be. If I wanted to construct a velocity versus time graph, and I was given an acceleration versus time graph, the way that I would do it is I would go to my velocity versus time graph and first plot v0. I'd have to know what that is. It's an initial condition. And if I want to know what the velocity is at this new position at time t1, I would go to the a versus t graph. I would calculate the area under this curve, and then I would add that value, that delta v, to v0, and that would give me v1. So you can see here that this is the approach of taking an AT graph and converting that into a VT graph. Similarly, if we look at the A to S graph, you can see that we can also perform an integration to get the V versus position graph. Now, this is a little bit different. It's a little bit more complicated because in this case, you can see that we have this acceleration versus position graph. But you may recall that the relationship among acceleration and position has this equation associated with this. Remember, it's the integral of ADS is equal to the integral of V dV. And so what happens here is that this says that 1/2 V1 squared minus V0 squared is equal to this integral, which is the area under the AS graph. So it turns out then that what you need to do is you actually have to solve this equation for V1. Now, just as we did in the previous case, it's assumed that V0 is known, and so really all we're doing is we're moving the V0 term over to the other side, and then we have to take the square root to get V1. So it's a little more complicated to do it this way. But so what you can see what's going to happen here is this. The approach is going to be, we'll know what V0 is. We'll go ahead and plot that on the V versus S curve. If we now want to know what V1 is, well, I need to know, basically, I need to come and solve this equation right here for V1. V0 is known, and I need to know what this term is. It's the area under this AS graph. So if I come over here, you can see all I need to do is just come in and get the area under that. And in this case, it could almost be approximated by a rectangle, maybe a rectangle and a very small triangle. So in that way, then, this is a different way of getting an acceleration graph. And note that this is going to be, it's a different way of working with an acceleration graph. And it's the case of where acceleration is a function of position. So as you recall from our previous lecture, lecture 1, we talked about the fact that there are really two different relationships that we have. We have acceleration as a function of position, and we have acceleration as a function of time. And so these graphs kind of help to illustrate those two different relationships. Now, the next thing we can then do is to look at a VS graph. And here you can see that we have this VS graph, and here is the velocity, and here's time. And now here I have the velocity, and here I am at some position here. And what I wanted to do here was to come in and compute the acceleration from this thing. we have the relationship that the acceleration is equal to v times dv ds. Well, if you look at this velocity versus position curve, you can see at any point we know what the velocity is because it's a velocity versus position curve. But then also, too, we can calculate the slope dv ds at any position. So what that means then is that if I take the velocity at that position and multiply by its slope, I will have this term which actually gives me the acceleration. So you can see at this particular point, if I wanted to draw the A versus S curve, and I had already a V versus S curve there, all I would need to do is start off with my A naught, that would be an initial condition, and when I get to this next time point here, actually this next S point, if I want to know what the acceleration is at that point, all I do is come up here to the V versus S curve, and I read off the V value, and then I also read off the dv/ds value. So here we have an example, and this is an example where we have a velocity versus time graph. Remember that we have been looking at acceleration versus time, acceleration versus distance, velocity versus time, velocity versus distance. This one falls into the category of velocity versus time, which is the more usual case. And so what they want us to be able to do here is they say, if we know the velocity versus time graph, could we then come up with the acceleration versus time graph and the displacement versus time graph? So let's think about that for a second. So how is that done? What is the relationship among velocity and acceleration and position? Right? So we said that basically what they are asking us here is what is going to be your plan of attack for this problem? And you know, just back from lecture 1, that if you start off with the position, if you take the derivative of the position, you get velocity. If you take the derivative of velocity, you get the acceleration. Working our way backwards, if you know acceleration, if you take the integral of acceleration, you get velocity. If you take the integral of velocity, you get position. Now in this case, they've given us position, and they want us to know, first of all, what's the acceleration graph? So if I were to look at this thing, if I want to get acceleration from velocity, do I take the derivative or do I take the integral? And this would be a case of where, if you don't remember, you might go back and look at your formula sheet to look to see what the relationship is between acceleration and velocity. Turns out that acceleration is the derivative of velocity. So what we would do then is we would go in, and everywhere along this curve here, we would come in and calculate the slope of this velocity versus time curve. Now, fortunately, this slope is constant in this region of the curve, and it's also constant in this region of the curve. So I can actually go in and just calculate the slope for this curve, and then also calculate the slope for this curve. And you'll also notice, too, that they have conveniently provided equations for these segments of the curve. Could you come up with these equations on your own? Well, we know here the velocity is equal to 30 times time. Well, another way of doing that would be to say, well, at this point, how much time has gone by? Well, 5 seconds have gone by. How much distance has gone over 150? If I take 150 and divide it by 5, I get 30. So that's how I would get this equation. Now over here, you would do a similar thing. You start here, you come down 150, and you go over 10 seconds, the difference between here and here, and that gives you your slope of negative 15t. So what's this other term over here? How come we've added this other term? Well, the problem is that if you want to know what the velocity is at this particular time right here, you can see that 5 seconds have already passed. And so in this case, we need to account for that, and that is accounted for by this other term over here. Separately, then we're also going to go in and look at the S versus T graph, and that's going to involve taking the area under these curves, and conveniently these are going to be triangles. So let's go ahead and take a look first of all at the acceleration. So you can see here that we have for this AT graph that when we are in this range right here, the velocity right here is going to be just the slope of this thing, which we said was 30 meters per second. That was this 30 times t. That's the velocity. So we got that slope. And so then that tells us then for that particular slope there, we can come up then with the acceleration there as being equal to 30. Okay, and because we're taking this this derivative with respect to time, we are getting rid of the time term there. The derivative of 30t is just 30, and that's why we have this constant acceleration. Now we're in this regime. We've already shown that this right here is the velocity curve. If we take the derivative of this curve with respect to time, the 225 term drops out, the t becomes a 1, and this becomes negative 15. So you can see here then we have constant acceleration in the first segment of the curve and constant acceleration in the second segment of the curve. So that satisfies the first case. Now, if we look at this second case where we're trying to come up with the position as a function of time graph, now what we need to do is to come in and integrate this curve. Now, we already have equations for this curve, and so you can imagine if you were going to be working with a curve like this on the example problems, the homework problems, why the first thing you'd have to do would be to convert this curve into an equation so that you could integrate it and take the derivative of it. Now, wouldn't necessarily have to do that because we know that we could, if we wanted to, just take the area into that. We could go in and make a triangle, and we know the area of a triangle, that sort of thing. That could work as well. But you may not always have this simple of a shape, and so it's good to be able to work with both the equations and the shapes. So you can see here then that we know that the position is going to be an integral of the velocity. So here we have this integral, and you can see here then that this is going to be this 15 t squared is going to be the position for this thing. So here we have it then. And you can see that when we're in this range from 0 to 5, well, this curve is described by 15t squared. Now, when we move to the next segment of the graph, we have this additional term over here, as we talked about before. We have the this negative 15 t, that was right down here, plus 225. Well, if we go in and integrate this, this is going to be 1/2 t squared times negative 15. And then over here, this is going to be 225t. And then, but now the important thing here is to note, in this second region of the curve, this thing starts at 5 seconds. So we're actually going to have to evaluate this thing from 5 to t. So when we do that, what happens is that this equation right here now ends up getting this additional term, which is what we get when we plug 5 into this equation. So that's why we have that additional term there. Okay, and so then what that means is that in this region of the graph, we now know what the position is as a function of time, and we've got an equation for it. Okay, so next we have a concept quiz, and this is a quiz I'd like for you all to do on your own. You've got the 4 choices there, and if you would like to know the answers to this quiz, please see me, or feel free to talk to your classmates as well. So now we have another problem. Okay, so let's take a look at this problem. We're given a v versus time graph, and they want us to find the acceleration versus time graph, but also the average speed and the distance traveled. Okay, now we haven't really talked about average speed and distance traveled in this lecture. That was covered in the previous lecture. So you may want to go back and look at your notes and look at the equations that we have for average speed and distance traveled. Okay, so you'll notice that what we have here is a v versus t graph. They want us to find the acceleration versus time graph and also the average speed and distance. So we're going to be working with several graphs. And so you might just think for a minute about how you might do that, how you might solve this problem. Okay, well, we remember that the relationship between acceleration, velocity, and position is that velocity is the derivative of position, acceleration is the derivative of velocity. And similarly, velocity is the integral of acceleration, position is the integral of velocity. They've given us velocity. We know that we want to find the acceleration versus time graph, so we're going to come in and get the slopes in these two positions. We're going to get the slope in this position, and we're going to get the slope in this position for acceleration. Now, what do you notice about the slope of this line here? What would you say about the slope of this line? The slope of that line is 0, isn't it? So you have 0 acceleration over that period there. Now, you'll notice you still have an initial velocity, so you're still moving, but your acceleration is 0. And then what happens here, you can see that you're actually going to have a negative acceleration. You're going to be slowing down there because ultimately, say your velocity is going to be going to 0. So you must be having a decrease in your acceleration. Okay. All right, so let's take a look at then how this is solved. So first thing we want to do then is we're going to find the acceleration versus time graph. And you can see here that in this first region here, in that region between 0 and 40, the acceleration is the slope. It's 0. Okay. Now we're in this next region here. We're going between 40 and 80. And so then the acceleration is the change in velocity over the change in time. Well, how much does the velocity change? It goes from 10 to 0. So we actually have a change of minus 10. And then what is the time range that this goes over? Well, this goes over a range of 40 seconds. And so now then our acceleration is negative 0.25 meters per second squared. So then what that says then is that in the first region of that graph, we have a constant acceleration that has a value of 0. In the second region of the graph, we have a constant acceleration, which is negative 0.25. Now let's go back and check our work, right? Because we know if I have a constant acceleration right here, that means the slope right here has to be constant. And you can see that it is. See, if this slope was changing at all in here, that would mean that the acceleration would also have to be changing. But because this is a constant, we're in very good shape. Now, there's some other terms that they would like for us to find. They want us to be able to find the distance traveled. Okay, so what we're going to do next is we're going to integrate that velocity versus time curve in the same way that we did before. We're going to go in and we're going to find the change in position over this range right here. So it's in this range right here. We're going to come and take the area under that curve. Now I know that if I just multiply 10 times 40, that would be the area under the curve, and that would be perfectly valid. In this case, we also have an equation. This says that the velocity in this region is equal to 10. Okay, now, so what we're going to do is we're going to integrate the velocity and the time here. So we have the integral of 10 times dt, which in this case is just 10 over this time period of 0 to 40 seconds. 10 times 40 minus 0 is 400. So these check out pretty well. Now the next thing we're going to do is look at the change in position over the time interval 40 seconds to 80 seconds. We're going to use the same equation for that. Now you'll notice over here they are using this equation 20 minus 0.25t. Where did they get that equation? Well, it's very simple. It's just right here on the plot. Well, that's okay, but where did they actually come up with this equation? Okay, so let's take a quick look at that. Well, you can see that when I'm right here at 40 seconds, my velocity is 10. Okay, so I want to make sure when I do this that I still have that 10. Now, when I go from here to here, you can see when I go from 40 to 80 seconds, the velocity is basically going from 10 to 0, and it's doing it over this range of 40 seconds. So you can see here that this would be a change in velocity of negative 10 divided by 40, which would be negative 0.25. So we see where the negative 0.25 t comes from. Okay, well, where did they get this 20? Well, you can see that at this particular point in time, this point in time still has to work. I still have to get a velocity of 10. So you can see if I take 40 seconds, and plug it in here, I'm going to get negative 20. So what this other 20 is here for then is it balances out and says, okay, well, at this particular time here, I'm going to have this other velocity right here. So once again, we have negative 0.25, excuse me, actually it was negative 0.25 times 40 would actually be negative 10. So that's what the 24 is. 20 minus 10 gives us 10, which is what the velocity needs to be here. Okay, so that's how they came up with this equation. They didn't really mention that to you, but you would have to be able to come up with this equation on your own, for example, on homework or an exam. Okay, so now that that equation is in hand, well, now it's just a matter really of just integrating it over its limits. And you can see here that the change in position now is 200 meters. And so now I can see that the total position is going to be 600 meters. I take the position from 0 to 40 and 40 to 80, I get 600 meters. So now then, that has satisfied one of the questions, which was what is going to be the total position, and then finally what is going to be the average velocity here. It's the total distance traveled divided by the time. And remember that this average is one of the equations from the first lecture. So the total distance traveled is 600, and then divided by 80, we have the 7.5 meters per second. Okay, and so now, finally working towards the end of this lecture, you can see that we're going to come in and do this exact same problem, only now, instead of working with a graph that has a straight line and then downslope, we're going to add this additional portion in and have an additional chance to practice that. And so what that will look like then is that you will go in and solve this problem on your own. Now, the answers are provided here and will be posted on Blackboard, but I encourage you to go in and solve this problem yourself first, and then go and look at the answer and check your answer on Blackboard. Now, here we have another quiz, and you can see that we have these two questions. I encourage you to go in and attempt this quiz on your own. And if you would like the answers, please see me or talk to your classmates. I think you'll find that the answers for this particular quiz is going to be fairly straightforward. Okay, and so now we are at the end of this particular lecture. So just to summarize what we had talked about during this lecture, we talked about the relationship among acceleration and velocity and position. And we said that those could be related to one another via graphs. And the primary way to do that is via position versus time, velocity versus time, and acceleration versus time. And to take either the slope of those curves or the area under those curves to go from one point to the other. We also showed a more advanced topic, which was if we had acceleration versus position or velocity versus position. And in that case, we showed that there was an additional step that needed to be taken, that it was either we would still be working with areas under curves, but we might use that area and plug it into another equation, or we might work with the position, the location on a curve and its slope at that curve. All right, well, that concludes lecture 2.